Hi, very good evening. I am Dr. Chandrasekhar Kumar from Muhammad Satak Engineering College Department of EC Assistant Professors. So we are going to introduce about IPC. IPC full form means Inter-Process Communication in QNX. So introduction about IPC, it is a inter-process communication which can have two process exchange. One is for data, one is for control, and another is for notification of every occurrence which is happening in between one process to the another process. While going for one process to another process, we have thread here, and the process is happening through this and reaching to the process B. So what will happen in this? We have to control the data, send the data. We have to see how the data is occurrence. So in introduction part, QNX support a wide variety of IPC. One is QNX core, which is API is unique to QNX, or which is low level maybe, which includes QNX messaging, QNX pulses, and shared mirrors. So this focus on this module. So POSIX and Unix is also well known portable APIs. So which include signal shared memory pipes like required by process, POSIX message queues, and TCP IP sockets which required IO socket process. This focus of the POSIX IPC course module. While going for topic number 1, message passings. So in QNX IPC we have native QNX message passings, which is client server based, which is bidirectional communications. While here we have client process and server process. So from one client process to reach to the thread process, we are sending message like MsgSend and MsgReceive. So once message received, again we have to reply to the client, it's received. So client sends request and data to the server, and server receive and process it. While server reply to client, client gets response and continues like that. So native QNX message passing also can have like a remote procedure call architectures where server threads run at a client priority, and which can have fully synchronization. How it is? A full idle server is like block till waiting for the message reply, and client block until server replies. So we can see with this how it can process. One is client process which have threads, and message is getting an entry and it pass to the server side, which is having a server process which will receive the message. Again it will process, again reply back to the client. So its message sends at last exist, or else it will block automatically. So condition 1, we can see how it is getting blocked when it is getting pass and receives. So we have like a state through client to server state. When it is in runnable mode, so message is getting sent, and send message data is getting copied here. After copied, it reaches to the servers, which has to reply like receive till it is in runnable state. If it is not, it will be like received block state. Again message is getting reply back, again data is getting copied and it passes to the client. If not received, still it will be like reply blocked step, and or else it will run and again it passes to confirm that. So like that, send after receive and block or idle server will process. So case 2, when sending before receiving, like it may be busy, so we have again client and server, so it will send the message using function and MsgSend functions and send the data receive. It will be till runnable state. Once it is copied and then it can receive, which is in running mode. Again server has to reply to the client. In between, data will be processed in time options and the time takes and sent back to the client. If not, again it can be in reply mode of block and which will be in running continuously. So messaging parts, we have connections and channels. So server receive on channels and client connect to channels. A client send to a server channel using the connections. So client and server can process like that. So messaging with multiple channel and connections is possible when a client may have connection to several servers. A server uses a single channel to receive messages from multiple clients. So client A, client B, we have server C and server D, where we have in client side multiple connections and we have in server side channels, like also many channels. Message passing through client servers. Server have like pseudocode. Create a channel means channel create functions. Wait for message. We have message receive function. In that we can perform process reply like message reply and go back for like more process. Client pseudocode also have like attached to a channel, that is connect attach functions, and send message. We have message send functions. So it can be like copy and replace. Message channels. The server can create a channel using CHID, like channel ID equal to channel create flag function. So client can send the message to server, which is possible in multiple thread also. So channel is attached to a process, so which can have any thread in the process can receive messages from the channel if it wants. When a message arrives, the kernel simply pick a message like receive message, messaging through to receive it, while flag is a bit filled. When we look at some of the flag on the next slide. So channel create flag we can see now. So some of the channel we can create in flag mode, like underscore NT underscore CHF underscore private. So a channel for a process which is an internal usage, it can create a public channel process for us, which can have like proc MsgR underscore AD underscore public underscore channel ability. So same like we have this blocking connection and disconnection of channel. So message can be in connect attach mode also. So the client connects to the server channels. So we have like connect how to server na CO ID equal to connect attach function of 0 PID, CHID, underscore NTO underscore SID underscore channel, flags functions. So PID and CHID is unique to identify the server channels. So PID is the process ID of the server, and CHID is the channel ID. So here always pass underscore NTO underscore side underscore channel for the fourth parameter index. Why it is, we can see from here connecting with connect attach quite. Connection ID quite come in two ways. One is for file descriptor, another is side channel connections in quite. So when we call connect attach function for self as opposed to only function calling it, so we do not need our core ID to be in the file descriptor range, where we can have passing message underscore NT underscore side underscore channel, which can prevent. So these are the examining synchronization thread. Message passing clients, message send function like call client. How we can check it as status? Status equal to MsgSend function of quite comma SMSG comma bytes comma or MSG comma or bytes. COID is the connection ID and SMSG is the process into the message to be sent. S byte is the number of byte of SMSG to send. RMS is a reply buffer for the reply message to be put into. R byte is the size of RMSG. So status is what will be passed is the message reply function's status parameter. Message passing server, the message like receive calls we have server. So RCVID equal to message receive function of CHID comma or MSG comma R byte comma information about that. So CHID here is the channel ID, RMS is the buffer in which the message is to be received into that. So R byte is the number of byte to receive in RMSG. It allows us to get additional information, and RCVID allows us to message reply function to the client. And we have message reply and call server. While passing to the server, we have like message error to the call server, which calls the message sent to return one state with error, and set to whatever is it in the errors. So how it can be function like message error function of RCVID comma error. So RCVID is the receive ID returned from the server, which is message receive call functions, and error is the error value to be put in error for sender. So these are the example we have for the server and client and message. How we can see this architectures. Message data is always how it is getting copy and sent through client to the server. So the number of byte actually transfer is the smaller client buffer size and the server buffer size. So here kernel does not pass any pointers. A server can reply with no data. So this can be used to unblock the client in case where we only need to give a status or acknowledgement back to the message send functions. So client knows the status of request. So designing for message passings, we have like message type. How do we design a message passing interface? So we can design or we can define like message type and a structure in a header file. So like both client and server will include the common header file. Start all message with a message type, have a structure matching each message type. If messages are related or they use a common structure, consider using message type and subtype. So it can define matching reply structure. So abiding overlap with message in QNX systems, which can have some types of message which is generated by QNX system library routines. Example, read function, pro_msgr underscore event underscore notify functions. All QNX messages start with uint 16 underscore t type, which will be in the range of 0 to underscore I underscore max 511. So using a value greater than I underscore max is recommended. So on the server side, how it is designed for server code, which is having branch based on type. So while loop functions, one we were passing with RCV received and equal to message received. So we are having function CHID comma and message comma size of function of message comma null, which is again getting switched over it message of MSG type functions. In case we have like MSG underscore type underscore 1 colon handling with handle underscore message underscore type underscore one function with like receive VID comma and message. So where we have break of this, and case we have to give for this message MSG underscore type underscore 2 and so on. So while passing the message, how it is getting, so we have like called pulses. Pulses is a non-blocking for the server sender side, which can fix the size payload, which can have 64 byte value, and 64 bit value can be treated as a pointer, long or integer, and there is 8-bit code which comes under 128 to 127, negative value reserved for system usage, and 7-bit for availables. So it is a unidirectional where no reply is there, so it is very fast and inexpensive. So where we can see it is passing through pulse. So sending the pulse are sent as follow, like MsgSend pulse function of quote, priority and code values, where code is 8 bits and value is 64 bits. So code is usually used to have like pulse type, which is valid range underscore pulse underscore code underscore meanable function of 0 to underscore pulse underscore code underscore max a function of 127. So to send a pointer uses MsgSend pulse ptr function instead. Priority indicate that receiving thread should run it. QNX uses a priority inheritance scheme to minimize the priority inversion problem, which can deliver order based on priority. It can have -1, which is used for the priority of the calling the thread. It can send a pulse across process boundaries, and the sender must have appropriate privilege for it. So I'll going for receiving pulses. Pulses are received just like messages with a MsgReceive call functions. So where a server can determine whether it has received a pulse vs dots a message by the return value from the MsgReceive functions. So the return value will be greater than 0 if a message was received. So this value will be the RCVID, which will be needed to MsgReply functions. The return value will be equal to 0 if a pulse was received. So we cannot MsgReply to pulse. So the pulses data will be written to the received buffer when the received buffer must be larger enough to hold the pulse structure. If not, the return value will be equal to -1 and error number will be false. So the pulse will be the lost here. While going for pulse queue, it is like by default pulses are queued until the system runs out of memory. So this may be a concern due to dropped pulses from places where failure isn't detectable when it is draining of system memory because of poor server behavior also. So this situation is to be pre-allocated the pulse queue for a channel. So this is the structure for this. So if more than pulses are queued without being received, then it will be by default the process is getting killed here. So this is the example for receiving the pulse. Send pulse structure. When received, the pulses structure has at least following member like code values, which having data like 8-bit and the value member is actually union. And receiving pulse, we have with the example like the server will have determined to region for this pulse by checking the pulse code here. So getting the information from the client after receiving a message, so it can have information stored in the struct. So how it is a struct underscore message underscore info, and it can get it during the MsgReceive like RCVID equal to receive chid or message or byte and info also, or later we have the like message info or receive it and info. So this will not be updated if we receive a pulse. It only contain old garbage data. So these are the message strict information keywords which can have PID, sender process ID, int TID, sender thread ID, int CH ID means channel ID, int SCO ID means server connection ID, int COID means sender connection ID. We have sort priority, sender to priority option. Sort flag means extra info we can have in this size underscore t, message alien, message length. So you have size underscore t, src message alien means message length, and size of t underscore t is we have dst message length means message length. So in detail about the message size info we have in this way, which can have number of byte copied will be the smaller of what the client send message with message send function and what the server received with message received. So similarly we have for reply also. So how a client find a server first, we'll check it. So for finding the server to a client, for a client to send to a server, it needs a connection ID, COID. So that is message sent function of QoID, and message direct. So as we have seen, to get a QoID, client can do connection attach functions. So the problem is, how does the client know what the server is? PID and CH ID. How does the client find server? In our print out its PID and CHID, and the client took them to a command line arguments. So this does not work well as a general function solution. So there are two other methods depending on whether the server is a resource manager or simple message receive loops. Both methods make use of the path name space. Server put name into the path name space. So both client and server have understanding of what that name will be. So client does an open of the name and get a QoID. So if the receiver is a resource manager, then resource manager attaches a name into the namespace like rsmj msgr underscore attach function of /dev/sound close. So the client does finding the fd equal to open /dev/sound in that. So then it can make use of the fd recall that fd are a particular type of QoID only. So we have write function of fd and read function of fd or MsgSend fd. So finding the server with name underscore attach function or name underscore open functions. So if the server is a simple like message receive in function loop, then it is like we can use name underscore attach function and name underscore open functions. So the server does like that, name underscore attach underscore t star attach semicolon, where attach equal to name underscore attach. We have the function of null comma and the name of that comma 0. The client having like QoID equal to name underscore open my name, where the name will be given and 0 data with this. So name underscore attach function create the channel for us. So it's having internally it does a channel create functions. When doing so far, it turns on several channel flag, and the channel flags request that the kernel send pulses to provide notification of various event. So it is code having where aware that it will get that these pulses or those pulses and handle them appropriately. So these are the channel create pulses in 3 parts: underscore nt underscore chf underscore disconnect, and underscore nt underscore chf underscore quad and disconnect function purpose, and we have like unblock functions. So tracking and cleaning up as per the client data, we have server often needs to track as per client data. Yes. So example for like pending requests, configurations, notification request. So these are three part we have here, which can persist as long as client is associated with the server, which also need to be cleaned up or released when the client goes up. So we have disconnect pulse tells us when the client has gone away. So it's a not have like longer connection for security purpose. So it associates the data with the client. So with the function message and input.scid. On receiving side, we have underscore pulse underscore cod underscore disconnect pulse. So it can find the matching data pulse on the pulse.cod, which can release the matching data, and while releasing the squad by calling connect detach, a function of pulse.squad. So we have next like multiple part for message sending. A multiple part messaging, if you want to transfer like 3 large message parts, so it can have various data size 750 kb, 500 kb, 1000 kb. So we should use like malloc functions, which is enough to have a space and which can hold the complete message of adding with all message sending part of data like 750 kb plus 500 kb plus 1000 kb, it around 2.25 MB. So while doing these three memory copy functions to produce one big message like part A, part B, part C, or part 1, 2, 3. So while going for continuation of message sendings with 3 part IOV with point to the data and using the message send B functions, which is having much more efficient. So avoid the malloc function and the memory copies. So we process through the message sent to the server 0, 1, 2 like. So it is very useful for scatter and gather situations. So IOV are having like input output vectors, so which can have array of pointer to the buffers here. So which is having very uses, avoiding copies when assembling messages containing multiple parts, where variable length message is there, like server does not know the size of the messages that the client will send, and write function message to the file system driver or server as use input output vectors. While going through the input output vector using message, instead of giving the kernel the address of the one buffer using message and functions, so which can have SMGS and which can void with or MsG, which is called buffer here, and which gives the kernel an array of pointers to buffer using the message and functions. So SI over here and RI over here, which is having array of pointer in multiple buffers, so which are a combination part also. So what does an IOV underscore T look like? So which is like type defined structures, and most useful as an array here IOV underscore T, which is having 3 variable function IOVs, which make the number of element which is greater than equal to the desired number of message parts. So using an IOV, we can have various data set like set IOV with a large number of data we can set here. When a server send or receive, these part are considered as one continuous sequence of bytes. This is ideal for a scatter and gather the buffer and caches. IOV are used in the messages functions that contain a V near the end of their name. So message can receive read V and message receive V, or message reply V, message send V, message send V, and receive V, like that function write V functions. So these are the variable length example for the client side write every comma and size of it. So we have header file and which can show the address length with buffer data. So while actually what we can get to the send, we have header 12 bytes and buffer 12 byte data, so it will be like 12 bytes plus 12k bytes buffer data. It is logically continuous blocking of bytes. So these are the other server side what we get to receive. So message we have reality through, we don't know how much byte it will be there going to be received until we have looked at the header functions. So this is how we can look into this data sets. And here this is the message passing call functions. So we have from client to server message and data passing and copy with logical process, how it is acting for all data in two parts and rest of data copying are not in kernel or by kernels because of server receive only a specific data bytes like 12 bytes. So we have like 3 parts, 4 bytes for each 3 parts which is getting escaped here, and alternatively logically it is sent to the 12 bytes escape to here and single buffers. So data is getting copied from client address space to server address by kernel itself. So and then getting more data later, it also processes with single buffers where send it to the space by kernels. So we have message write function from copy to the client, and these are the write byte from the server to the client, but unblock then client. The data from message is getting copied to the client and reply buffer. So they return the number of bytes actually copied to and complete the message exchange. So thank you so much. So in this application of QNX IPC, we have in automotive control system, medical device, industrial automation, robotics and avionics we have. So conclusions, QNX IPC is reliable, secure and real time, which is enable efficient in communication between process, which is suitable for safety with very critical applications. So thank you so much.